You can please turn on your cameras. Attendance, let's see here, period. Roland, Julian, Dorothy, Kylie, Matt, William. All right, we're going to go over that homework problem. At this point, the homework problem was the loop-the-loop problem. Here's our loop-the-loop. We'll get to test the result of this loop-the-loop problem right here on this apparatus. I believe I've shown you in the past. It's metal. It's made of metal. The balls is these are stainless steel balls, ball bearings. So it's metal on metal. I wouldn't expect it to be that frictional, but I don't know. Let's see. What is the coefficient of friction for metal on metal? 0.6 to 0.15. That's a backwards order, but okay. 0.15 to 0.6. Oh, there we go. Coefficient of kinetic friction around 0.09. Not to mention it's not sliding, it's actually rolling. That's a whole nother topic, which I'm not going to get into now. But it's a very small amount of friction, but not zero. Not zero. Nothing zero. You can't. I mean, at least that's what the current wisdom of physics is. That you cannot make zero friction. You can't make anything be truly frictionless. You can get it close to that, and you can do things to reduce friction significantly. But according to the laws of physics, a frictionless surface is impossible. The reason is because a frictionless surface has to be perfect, and there's nothing perfect. Everything has flaws. Because again, on the microscopic scale, the surface of something that has irregular bumps and grooves and such is what causes the effect of friction. So to actually truly have a frictionless surface, it would have to be so smooth that there's not a single little irregularity along that surface. Even NASA, who spends millions of dollars to create these mirrors for their telescopes, NASA's mirrors telescope. I mean, look at these things, right? These are massive mirrors that get installed into their telescopes, and in fact, it's a composite, kind of like a fly's eyes that has a variety of mirrors that are all attached. All looks like they're all hexagonal in shape. They go to great lengths to make these as smooth as they possibly can. They literally have people in white suits, like you're seeing here, that literally stand over this glass. Look how smooth and shiny this is. And literally, like they have sanders, but not like a wooden sander, but similar, but it's made for glass, with the intention of getting it as smooth as you possibly can. Because any irregularity in that glass will reflect the light in a way that it shouldn't. If it's perfectly flat, then it will reflect it in the appropriate way, and you'll get wiggles in it, then it's going to reflect the light improperly. And then when they go look at that image, you'll see irregularities in the image. Even for them, who spend millions of dollars and months trying to get that as perfectly smooth as they can, They admit it's impossible. You cannot get something perfectly smooth. When they scan it with a laser after they're done, they realize there's still some irregularities along the surface. They're down to the nanometer. These people can probably get down to the micrometer or the nanometer, meaning there might be one spot on the glass that is 1 micrometer higher than another spot next to the glass. Touch it with your hands, it's going to feel perfect. Look at it with your eyes, looks perfect. On the microscopic scale, they admit it's not perfect. And that's the reason. You can't have something be frictionless because it would have to be perfectly flat. Nothing in the universe has ever been found to be perfect. Every single thing has flaws. Perhaps a good life lesson to be had there. That doesn't mean don't, shoot for improving yourself. You should. But if you expect yourself to be perfect, I don't think that's a good idea. So I'm going to go over this problem with you. Again, it's metal on metal. It's very little friction. Of course, there would be some air resistance. It's fairly small. I mean, it's smaller than my thumbnail. Air resistance is primarily affected by the width of the object that's moving, called the cross-sectional area, and how fast it's moving. So the cross-sectional area of something like cross-sectional area of this, if it was moving towards you like this is the area that we're talking about. If it's moving towards you like this, then this is the area that we're talking about. It's the area facing the direction of motion. That's the area that runs into the air, of course. And so that area depends on the orientation. And then the shape of the area, this is curved, so this would have some nice aerodynamic properties, allowing the air to kind of smoothly flow over the bottom and top, still impacting it. As it moves, the air still impacts it, provides it backwards force, but less than something that's perfectly flat. And certainly something that's spherical is what we consider very aerodynamic. So the effects of air are low on this already because of its small shape, small amount of area for the air to run into, and the fact that it's actually spherical, which is one of the best possible shapes to reduce drag. That all said, it should be pretty close. For those reasons, it should be pretty darn close to whatever we calculate. Again, when we calculate, usually we're saying, again, let's assume that there's no friction. Let's assume there's no air resistance. Let's make our calculation. Why? Because it's far too complicated to calculate it at your level. If you want to include air resistance, and I was just talking about this with your brother the other day, you have to be able to do what's called differential calculus, differential equations. The reason, and it's not just the calculus level, it's calculus 1, calculus 2, calculus 3, and then you have differential equations. And you would do those in college. Many of you will. Differential equations are hard. And the reason is because, let me give you the example. Air resistance is actually the effect of moving through air, which pushes effectively backwards on your body if it's your body that's moving forward. That effect of the air impacting you and pushing you back, drag, air resistance, it's proportional to v squared. It's actually a quadratic relationship. So the drag force, the air resistance force, is proportional to the square of your speed. So in this case, if this thing's rolling down, which we know it's going to speed up, speed up, speed up, speed up, where will it feel the greatest drag force? Actually down here, when it has the highest speed, it will be running into the air with the fastest speed, and therefore the air will be running into it with the fastest speed. Who can claim who's moving? The air says you're running into me. It says, no, you're running into me. That's the whole point of reference frames. But either way, they're certainly colliding with the greatest speed, the ball in the air down here. So there's actually more effect from air resistance here, more of a drag force, which would be a longer vector. And as you go up this ramp, that vector would get smaller and 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 smaller. Like, wow, that's complicated. That means if you wanted to know the exact acceleration, it's simple when you know the forces are constant. Like this vector doesn't change and this vector doesn't change. We can do the vector sum, call it the net force. And while it moves, know that the net force doesn't change. Hello, AP Physics 1, which is all about constant things because that makes it easier. You'd say, wow, how would I calculate the net force? If the upward force from the air resistance is actually small here, and then that upward vector gets longer and longer and longer for every little increment of movement and every little extra speed that it gains, how do you deal with the net force? And that's why it's complex. It's difficult. That's not only difficult, it's really difficult. It takes, differential calculus. Many of you guys will learn that for sure. Not as freshmen. You'll learn that as a junior or senior. So it's out of the scope of our abilities in this class. I'm just telling you that's the reason why. We always say, let's pretend that there's none. And in this case, the effect should be pretty minimal anyways. So what we do here should be pretty close to what we see. That's what we're going to find out. First, I'm going to go over it, if I could. Bear with me for one moment. Let me grab my piece of paper and grab the slide. All right, and let me just grab a I think the green marker is working fine. Let's try the green marker. I am presenting, right? So I don't have to switch my screen. Can someone just say yes to that? I am presenting. Because when I go to this program, it takes away that sharing button, so I can't tell. Can somebody at home tell me if I'm presenting my screen? Should be.
We can see it.
All right, thank you. All right, thank you. All right, let's just. All right, so let's tackle it. Tough problem, I'll tell you, it's a tough problem. When I worked at UMass, well, I went to school at UMass, I worked there as a tutor in the tutoring center, which was a great part-time job. If nobody showed up, I could just sit there and get paid to do my homework. Great, good deal. But I remember a lot of students coming in with this problem, and they struggle with it because it's a hard problem. It's challenging conceptually to think about and to work out. That's actually when I realized I loved teaching, from doing a job that I thought was just going to be a little $12 an hour job or whatever it was back then when I was working, and then realized I really liked teaching. I enjoyed it. When I was gotten involved with teaching something, I was like, wow, hours go by and it feels like minutes to me. Wow, that was 2 hours. Like, yeah, that was 2 hours. We were just like, holy moly. But I liked it. At that point, I said, you know what? I'm not going to be an engineer. I'm going to be a teacher. Maybe it's a calling. My dad was a teacher too. He was a physics teacher, and he also went to school for physics. All right, let's begin. Here's the problem. All right, the first question, or the first thing we have to think about is when it's at the top like this, we have to consider what the minimum speed is. Remember that if it's too slow, it's just going to come up like this, and then it just literally it climbs, and then it just crashes down like this. A little. If you raise it a little higher, it'll have a little extra potential energy at the top. Of course, that will translate into more raw speed at the bottom, which will cause it to be able to climb a little higher the next time, but maybe not quite enough, and it still comes and crashes down. At some height, of course, you're like, I just got it, because it actually did come off a little bit, but it actually recatches here, and then boom, and it comes around. You're like, well, I got it. That's the concept of minimum speed, right? There's some minimum speed, but at that minimum speed, it literally loses contact. It literally comes off for a brief moment, literally a fraction of a second, and then reconnects with the track. And that's a key piece of information to solve this. Because if we're interested in what is the minimum height, we have to correlate these two, right? Is the speed at this point correlated with how high you brought it? Meaning, does a lower height correspond to lower speed here, where maybe it doesn't even reach there because it didn't have enough speed? Or a higher height, does that correspond to a higher speed here? Yeah, they're totally correlated because this is a potential energy thing and this is a kinetic energy thing, right? And so there's a connection there. So our first job is really to think about circular motion. So what I recommend is you just memorize, which I'm not a big fan of it, but there's some things where I'm like, just memorize it. Just do it. It'll help you. This is a very useful formula. I don't think it's super duper long. It's just worth memorizing. There's a lot of cases where you can solve problems on an AP exam, especially multiple choice, and they don't care whether they're like, good for him or her. He memorized it, good for it. If it's a free response question, maybe they'll ask you to derive it, but probably not. There's plenty of problems, even in free response, where you can be like, boom, here's my formula, I'm just going to use it. They give you the points. unless they say, again, derive something. If they're very specific that they want you to prove something. But otherwise, this is extremely useful. This is the minimum speed required to get around this loop with this radius, r. It's a function of r. G is just G, right? Meaning that we'd get different results on different planets, but for now we're stuck on Earth, so we don't have to consider that. But it's just a function of r. It depends on, is this a something that looks like this, or is this something that looks like this? Which one do you have to bring to a higher height to successfully get around the loop? Well, mathematically, you could say, well, if this is the formula, r is, and these are proportional to each other, less r, smaller circle, here's little r, less r, less speed is required at the top. Less speed at the top means I can bring it up to a lower height, and it'll still go around it. But just thinking about it, right? The speed is in a tiny little loop like this. If it's only an inch from here to here, then the speed at the bottom loses a little bit of speed as it climbs, but it's such a small distance, it's not going to lose that much speed. So for that reason, you can probably just drop it from here, and it will go around. Where on these big guys, there's a large loss of speed. This is a big hill for this thing to climb. There's going to be a large loss of speed and kinetic energy as it climbs, and that's something we would have to compensate for by bringing it up much higher. But let's do that. This is the top of the circle, and we're saying that the ball separates, moving sideways, but there's no Fn is 0. This is key. The normal force equals 0 at v min. When it's moving with a speed of v min, the normal force is 0 because the normal force is how hard they're pressing against each other, how hard the track is pressing against the ball. But at the minimum speed, it separates actually for a brief moment there, which means that the normal force is 0. We can still draw it up and say, all right, there would normally be a normal force down. There would normally be a gravity force this way. I'm not drawing them relative to each other. I'm just identifying there's technically two forces. Only two. They're both plus because the rule for circular motions is that any force towards the center of the circle is plus, away is minus. So then we say that the net force equals mv squared over r. Other textbook write Fc equals mv squared over r. Even other textbooks write the sum of the radial forces equals mv squared over r. There's all these different ways of writing something. Just know that it's the net force. As long as the combined effect of all of the forces comes out as in the direction of the center of the circle, in amount, quantity, magnitude of mv squared over r, that thing will stay at a constant speed as it passes through that point and stay at that distance. It'll maintain that curve. So with that in mind, we're just going to do that. We're going to say that I'll just keep it simple with the notation. F net equals mv squared over r. And again, we had two, Fg and Fm. They're both represented as plus because they're both, again, that's the rule. They're both towards the center. Just like we have rules for sideways motion. To the right is plus, the left is minus, and we just stick with it. Well, this is the rule for circular motion. Inwards is plus, away is minus. We say at minimum speed, at v min, Fn is 0 because it separates. Therefore, this is the number 0. I just plug in mg for weight, mv squared over r. The m's cancel, telling me that I should be able to technically do this experiment when we do it in a little bit. With two different balls, they can have different weights, and they should technically have the same height that you'd have to release from. Technically, if one of the balls is much wider, though, it would actually have more air resistance effect because it's wider. You might have to account for that and then have to raise it up a little higher. But technically, if you could have two identical balls that looked identical, but one was more massive, that means it's more dense, they should technically have the same h min point where they just barely succeed in getting around the loop. That's why m is canceling out. And that's where this result comes from. And as soon as you cross this out and say this is 0, that means you're referencing V min. This becomes that minimum speed, because only at the minimum speed will it separate. Only at that minimum speed does it separate. So as soon as you make that assumption into the formula, you got to reference that's only at the minimum speed. So V squared min equals RG, right? V min squared. Now, again, I don't recommend really necessarily deriving that in an AP exam. At least see it, be aware of it, but memorize that. Memorize it. Again, it works for anything that's going around the loop. It can be the motorcycle problem. They show the guy at the circus and he's going around in his motorcycle. It's the same thing. Doesn't matter if it's a motorcycle going around the loop, a ball going around the loop, the bucket problem that's being swung upside down. They said they don't want the bucket to fall, the water to fall out of the bucket. An amusement park ride, and they say they don't want a person to fall out of the roller coaster. They're all the same. Memorize that. So now let's use it. See, how do we use that? Because that is useful thing to know. So now when we say to ourselves, all right, up here at the top, somewhere up here, we know that the total mechanical energy is potential plus kinetic. That's just an idea that it has some total energy called total mechanical energy. The sum of those two. And then here we know that's also true. I'll call this, I guess, F, and I'll call this I. I'm just arbitrarily writing UF plus KF. It's just like a stamp. It's like as generic as it gets. Let's stamp it on there, and then let's work with it to see how it plays out in this particular problem. At the top, we know when we release it, there's no potential energy. There's no kinetic energy because it has no speed. That goes away because that's 1/2 mv squared, right? 0 for V. So the total energy at the top is just the potential energy, mgh initial. Here, it actually is moving along. It does have some kinetic energy. It does have some height. By the way, that's a little tricky. The height is 2r. To solve this problem, you have to reference this height measured from the ground as 2r. It's 2 radii high. Since the problem says express your answer in terms of r, h here has to be expressed as a function of r. 2r high. 1 radii, 2 radii, 2r high. That's key. Which I kind of gave you that hint, I think. But let's just see how this plays out. Again, I can't cross out potential energy because it got some height. I can't cross out kinetic energy, got some speed. And now we continue forward. Conservation of energy says that if there is no loss of energy, which we're making that assumption and approximation to be pretty close, because if there is some loss of energy when I do it, it's a tiny amount. You can always compensate for that for raising it up a little higher to replenish that loss of energy we anticipate it will experience as it goes down the ramp by just giving it a little extra potential energy, a little extra height. But again, we're assuming that there's no loss. So the original energy is just mgh. Then when we get to this part, we'd have to say that the final potential energy is mgh, final, plus 1/2 m e squared. That's generic too. That's just a generic stamp. But now we have to make it special to this problem because remember, h is actually 2r. That's how high it is. So I'd end up putting mg 2r in for h. And then the 1/2, oops, I didn't mean to put equals, plus is what I meant to put. And then the 1/2 m, this is going to have to be v min. We're going to have to make that special to this problem because we're trying to find out whatever this minimum height is, which corresponds to a minimum speed, we said, right? So if I'm referencing the kinetic energy here, that has to be the v min. So let's plug it in. That's just the right side of the formula. It's our second point of interest, this point here. All this has to go in. I'm going to write the 2 first. 2rmg. Doesn't really matter which order you do it in, but all right. So there's that piece. And then I have a 1/2 mv squared. All right. Plus 1/2 m v min squared. Now we can see if we divide all terms by m, the m goes away. Again, meaning that any marble with any mass, as long as they're relatively the same width, should yield the same result. Drop them from the same height on the track, they should just barely make their way over. You don't have to adjust it based on its mass. Now remember what our result was that I said, hey, memorize this, or at least I recommend it. V min squared equals RG. V min squared. Ooh, that's nice. That means I can just stick square root of RG right there. Is that obvious? Not at all. That's part of what students would struggle, and I struggle with. I didn't know how to do this right away. Struggle with it too. Everybody does. But struggle is good. There's some struggle in life that's good. If it's intellectual, then it's good. So I'm subbing in V min squared is equal to RG. It's true that V min is equal to the square root of RG, but V min squared is actually equal to RG. Let's just plug in V min squared because it's a 1/2 MV squared. Boom, RG. All right, let's just kind of polish this down now. Let's see what's left. We have G and an H. I have a 2G, I'll put 2GR plus. And then I have just this, really, right? The 1/2, I just tucked the 2 underneath. I'm allowed to do that. And then I just plugged away MB squared, V min squared, just put RG there. So it's just RG over 2. Oh, it looks like G cancels out. Maybe we do get the same result on any planet, whatever G is, or go somewhere, inside the Earth, actually G decreases. Strange. Weird, but G actually for Earth gets less as you dig a tunnel down towards the center. If you're interested in understanding that, email me. Otherwise, just know that it's true, which means if you took this experiment down that tunnel, it should give you the same result way down there where G is actually less. That's what it means. G doesn't affect this experiment. G cancels out. All right, let's see what's left here. H initial, which is where we start on the track, the top of the track, equals 2R plus R over 2. That's nice. Wow, all that complexity, and it comes down to be so polished. Let's just call this 1/2, right? Really, R over 2 is a 1/2. So really, I have 2 of something plus a 1/2 of something. The something is the R, but who cares? It's just 2 pizzas plus a 1/2 a pizza. 2.5 pizzas. Here, the pizza is the R. So really, we have 2.5 R's, right? Because we're adding them. And we know that we do, times and add plus 1. I'm teaching my son this actually right now. 2 times 2 is 4, plus 1 is 5. So that's really 5 halves R. Interesting. So our starting point should be 2.5 times greater than whatever R is. We said it had to depend on R. So if we knew what R was, let's just say R was 10 centimeters. I mean, again, 5 halves is the same as 2.5 R. So if R ends up being 10 centimeters, then 2.5 times 10 is 25 centimeters. I'll then start at 25 centimeters up the track, hold my breath, and let go. All right, let's give it a try. I obviously have to measure it because you'd say, you didn't do that already? No, I didn't do that already. Sorry. Right, let me move this stuff out of the way. In fact, so let me close this. In fact, before I do, are there any questions about what I was just showing before I close this out? Because I'm going to turn my other camera on. Any questions about any of this? If you tried and did not succeed, good job trying. I remember struggling on this one for a while. I didn't get it. I eventually had to go to somebody and ask them. So if you struggle, don't worry about it. It's a hard problem. But if you tried, pat yourself on the back. No, if there's no questions, then all right, I'm gonna change my camera. In fact, what's my best choice? Let's just sorry. Minimize the whole thing. Oh, my camera's here still on. I didn't know that. All right. So I have to think about how I'm going to do this. I think what I'll do is I'll move you guys over, and then I'll do the experiment on the tabletop. After we're done, I'm giving you I guess it's the first real AP problem to work on in class. Meaning like an actual straight from an exam. I copied it and PDF'd it, and I'm going to give that to you and let you guys work on that in groups. And I'm going to start, by the way, doing more of that. I usually wait until halfway through the year to do that, generally. And the reason is, I'll tell you, because I could be teaching kinematics and say, all right, give them some problems from the AP exam that you see, free response questions that are kinematics. There are none that are just kinematics. For every free response question you find from, let's say, 2013 that looked like it was kinematics, you realize that part D is actually an energy question and part E is actually a momentum question. And you're like, I can't really give this because they don't even know any of that stuff yet. So for that reason, since all of their free response questions are so multi-topic, I don't know if that's a word, but many topics in it, I usually have to wait. But we're at that point where you guys pretty much know enough where you can start doing them. And the good thing is that I get to give you the actual rubric because they post the rubrics online. And then you can look at your own work and really come to understand how these graders grade. It's brutal. Their grading is brutal. It's either there or it's not. There's nothing in between when they're looking at your work and grading it. All right, so let's see if you guys can see. Maybe I'll bring it a little closer. Actually, let me move this down one more. Better. Tilt it up a little more. All right, let's grab the meter stick. Move this a little bit. Oh, wrong way. Okay, my meter stick is, it's got one right here. All right, let's measure the diameter, right? That would make the most sense, and then just divide it in half. I mean, because otherwise then I'm estimating exactly where the center is. Always pick reference points that are obvious. The two ends of a circle you can easily measure. So let's do that. That should be more straightforward. I'm getting a radius of 20. See, and now this becomes some of the details, right? Like, you'd have to start saying, like, exactly how am I actually, this is like the real world, like, right? When I draw the circle on the paper, it's just a line, and then you come in the real world, it's not a line, it's a track. Like, and these are the details that get lost in translating problems that are real to paper. My point being, like, what do I choose here? It's got a thickness to it, right? So, and so does the ball. Like, does the ball take a role here in me measuring the diameter? If not, where do I measure to? Do I measure to the outside? Do I measure to the inside? What do you guys think? Any suggestions? What's that? Yeah, I agree. It would have to be the inside of the circle. The other detail that usually gets lost in translation is that, what if this was like not this, but like a big ball, like a big ball, real big, but still able to somehow roll around this? Then you might wonder, like, would you actually think about the center of mass? Would R actually be from the center of the circle to the center of mass of the ball? Any guesses? Any guesses on that? Or do we just ignore it? You always just measure it like this. So in that case, if it was really big, you really would actually have to measure to the center of the ball. I mean, I don't think they'd ever give you a problem like that. But when those kinds of questions arise in physics, the correct answer ends up being measured to the center of mass. In fact, when I did the pendulum problem with you the other day, the length of the string had to be from the ceiling down to the center of mass of whatever I was hanging from it. So if it was like a human, and there's a physics MIT professor that has his lectures, or Walter Hewitt, what am I saying? Walter, God, I can't remember his name. My brain's not working. Walter Hewen, I think his name is Walter Hewen, but he was one of the best physics professors of all time. He worked at MIT. He might have actually sadly recently passed away. All of his lectures are all on YouTube for free. He's amazing. I've watched every one of his lectures like 100 times. And they have this massive, MIT has this massive lecture hall, and he, like, for his pendulum things, he like literally has a massive pendulum, and he's literally swinging across the whole entire room. He's trying to demonstrate that mass doesn't really affect the period of the pendulum, how quickly it swings back and forth. But in that case, like, it's not just like a little thing. It's like it's a human being. Like he is the thing on it. And he points out, like, well, you would actually have to measure from the top of the ceiling straight down to my center of mass. And he points out when it's a big item like that, it makes a big difference whether you do that or not. Good lectures, by the way. Really good. All right, let's just measure this. I think I'm measuring 19 and a half. I'm measuring to the inside of the track. Inside of the track, because that's where contact is made between the ball and the track. So 19 and a half. All right, that's good enough. So let's, in fact, can you guys calculate it? Can you maybe try to calculate it now with that just that number? The radius, I'm sorry, the diameter of my loop-de-loop is 19 and a half centimeters. Walter Lewin. Something's not right in my brain. And I watched so many episodes, or not episodes, lectures of this. How can I forget his last name? Not Hewen. Walter Lewin. Lewin. Best physics professor ever alive. All right, can you guys calculate? Let's see. Well, 5 halves, right? It was 2.5 times the radius. I don't know the answer. I have no idea. Let's, where's my calculator? Where is my calculator? I lose my calculator? Oh, there's my calculator. All right. So what did I say? 19 and a half centimeters. But remember, we have to be in meters, right? So 0.195 in meters. Divide by 2. That gives me my radius, which is just slightly under 10 centimeters, which makes sense because it was just about 20 centimeter diameter. And then we had to do 2.5 times that, 5 halves, 2.5, so times 2.5. I get 24.37. I'll round off to 1 decimal. So 24.4. I mean, because, you know, you have to always remember, like, what's the practicality of those digits, right? Like, if you were looking, if I said 23.3 centimeters, what does the 0.3 represent? 24.3. Like what is a tenth of a centimeter? A centimeter divided into 10 units, pluck out 1 unit. How long is that? What do we call that? 1/10 of a centimeter. It's actually a millimeter, right? And so a millimeter, when you're looking at these meter sticks, I mean, these are millimeters. These little tiny lines, all those little tiny lines on there, I couldn't measure less than the difference between 1 millimeter. I mean, those tiny, you can't even, on their camera, I can tell you can't even resolve it, even tell. It's so tiny, like a thickness of a hair. So I'm just pointing that out too, because you end up with students coming in that, you know, want to keep everything. They write down 24.75893884. I'm like, I get it, because you're just trying to keep track of it and you love numbers and you love math. But I always want to point out, like, at some point, when you're applying it to the real world, your measurement devices only are so precise. You know, so for me, practically speaking, to go more than 1 decimal doesn't even make sense, right? My device, the meter stick, only goes to the 3rd decimal, right? So that means that those other decimals after the 3, because I got 0.243, are not significant. They're not useful. Usually that's called, you know, significant digits if you've taken a chemistry class. And it kind of makes sense when you think about it. So anyways, I'm going to do 24.4. All right, let's measure 24.4. Before I actually release it, could you just say, like, wait a minute, isn't it going to just be at the same height? Like, if this is where we need to get through with the ball like this, shoom, then can't we just release it right here at the same height? What would need to be true for that to be true? What would need to be the, like, what assumption would we, oh God, what assumption would we need to make? Oh, like, what assumption would we need to make for it to be true that releasing it from the same height as the top, it'll get around the top? In which scenario would that actually be true? If the potential energy here is mgh, and the potential energy here is mgh, and the conservation of energy is true, then the total energy that I start with should be equal to the total energy that I end with. Why can't we just, why could you make an argument that it can't be right at that height? Is there an argument you can make for that? Number one, let me make the point, when it passes through this point, is all of the energy potential? No, some of it's actually kinetic. In addition, you're losing some energy due to air resistance and some friction along there. So it has to be higher. Right? It has to be higher than that. 24 point, I don't remember. Was it 0.4 or 0.3? 0.4, was I rounding to 0.4, was it? 24.4. All right. Oh, just drop it already. I know. 24.4. 4 point. All right. So the other thing I have to be careful of is the thickness issue. If I'm measuring from the bottom of the wood, yet this bottom track actually has a thickness, I think I'd actually have to measure from the inside to get this just right, which I would like to do if I could. So I'm actually going to place the meter stick in the track, so it's not on the wood, and then do my best to just trace this visually over 24, and that's not very accurate, but I'm going to give it a go. It looks like, in fact, one more second. I know, I'm sorry that it's taking a while, but I mean, you only do this once a year, so might as well try to get it right. 24.4 would put it back in the track. Here we go. 24.4. Don't take my eye off it. Don't take my eye off it. All right, I kept my eye on it. All right. I think I've got my spot. In fact, keep my thumb there. Can you do me a favor? Can you come over here and grab that black marker? It's right next to my mug, my green mug. Can you put a little dot, like this nice little gentle, just so that I have reference of that? Perfect, thank you. All right, now I won't lose that. So it is, I will tell you, higher than the top. That point that I'm going to drop it from is actually here. It's actually, this is the top, and it's up here. All right, should it get around? I don't know. Remember, we assumed there was no friction, no air resistance. Let's find out. No, it does not get around. Got up only to about here. Oop, I lost it. Try again. Only about to, but little over half, up to about here. And then it comes down. So what will I need to do? And why do you think it's not making it? Again, loss of energy. There's loss of energy due to air. It's small, but how much will I have to increase this height to actually compensate for that energy loss due to friction and air resistance? Let's find out. I'm going to go up by about 1 inch. Oops, sorry, it's hard to try again. That's still not. Let's try maybe 1.5 inches, about right here. Still not getting it. 2 inches maybe. And I can't get it. Does it have to go all the way to the top? Let's find out. It clearly clears it when I release it from the top. Let's go lower. Still made it there. Let's see and find out where is this actual minimum spot. Let's try here. Still made it there. That was it. That's the spot right there. A little higher and it goes around. So that's it. So let's see, what's that end up being? Now the interesting thing is I'm going to ask you to think a question that you can think about. I'm going to measure that difference from where we predicted to where it actually was. Ends up being 8 centimeters. 8 centimeters higher than where it was supposed to be. What would the AP final question be? Calculate how much loss of energy there is due to air resistance and friction, based just on that information. And I'd like you to try to think about that now, just by yourself. Their final experimental question would say, in the real world, we find that we have to lift it 9 centimeters higher than our currently, our previously predicted value, where our previously predicted value assumed there was no friction and no air resistance. In the real world, we find that we have to lift it 9 centimeters higher than that point. Calculate how much energy is actually being lost in the real world when we really did it to air resistance and friction. So think about that for a minute. How would you do that? You have to raise it up higher vertically. That's extra potential energy, right? So you're making up for a loss of energy, kinetic energy technically, due to friction and air resistance, but you're making up for it by just raising it up a little bit, putting a little extra potential energy into it. And you don't even have to calculate it. I just wanted you to think, like what would you write? They would probably say, explain how you would, or how would you determine it. You don't have to try to calculate it. If you want to, you can. Actually, you can't. I don't even know what the mass of this ball is. I'd have to give you the mass of the ball. So just thinking it through, what would you write? And then as you're doing that, I'm posting this group problem that you guys are going to try. It's already there, so I should be able to. Oh no, I still have some other parts here to explain, but I'll still post your group problem. Class ends at what, 10:10? So I posted that. If you could figure out how much extra potential energy you gave it, that is the amount that you actually are compensating for. So if I raised it by 9 centimeters, which is 0.09 meters, if they gave me the mass, they'd have to give me the mass of the ball. And so I know M, G, and I know H is delta H. It's just the extra little height I had to give it, 0.09. I could technically do the calculation, M, G, H, plug the mass in, times 9.8 times 0.09. If it came out as 2.1 joules, that means it must actually be really losing 2.1 joules of energy as it pushes through the air and rubs against the track. When I really released it from the original calculated position, it lost 2.1 joules. So then you'd say, all right, raise it up higher to the point where it's now got 2.1 joules more potential energy. It should really add that loss of energy back into the system, and you should make it around, way of compensating for it. That's the idea there. Last questions I'm going to go over, and then I'm going to have you guys try this. Other questions are free body diagrams. In fact, let me return to this if I can. Un momento, por favor. Un momento. Okay. It is okay. So for free body diagrams, I can move this over. Sorry. There we go. So what's the first, that second, draw a free body at the top of the loop. So at the top of the loop, the free body diagram is literally just a downward vector, which is the gravity force. So that will be the answer to question 2. It's just, if it comes off of the actual track, then you can't draw the normal force. At Vmin, it literally leaves a track, right? So the only force is Fg. So that's what you'd have for the free body diagram. That's why when we did the equation, it was mg equals mv squared over r. And then we crossed out m and we got v squared equals rg. Because the only force is mg, which is providing that requirement of mv squared over r. For the next one, it says, draw a free body diagram for the ball at the top of the loop. What's the difference? Draw a free body diagram for the ball at the top of the loop when it's released from H-min. All right, draw a free ball at the, sorry. If it's greater. So if it's released higher than that, then it won't separate. If it's released higher than that, then it has more energy and it'll have enough speed at the top to get around the top without separating. And that means there would be some downward normal force, because if it's not separating and it's in contact with the track has to be pushing, on this case, down. So for that next part, you'd have FG and you'd have FN as both downward vectors if you released it higher than Hmin. How long FN is depends on how high you released it. If you released it way up there, this thing's got a huge speed coming around. It's going to really press on the track. FN would be really long. You can't really say how long it is. It depends on how high you bring it. But generally speaking, these are just going to be down. That's question 3. For question 4, what assumptions have you made when deriving the formula? That, again, air resistance and friction are relatively minimal. In the real world, should the ball release slightly higher, slightly lower, or right at the height to compensate for that? A little bit higher, because we're adding extra potential energy, like I explained, to compensate for the loss of the system's energy due to friction and air resistance. Question 6, draw a free body diagram for the ball at the bottom of the loop, being sure to draw vectors relative to their magnitudes. So at the bottom of the loop, as it comes around, that normal force is always greater than it weighs. That's actually always true. So down here, the normal force would have to be longer than mg. Once it rocks back and forth and settles and has no speed, FNs get slower and smaller, and then it just matches mg, and then it's just sitting there. But any amount of speed as it comes through this bottom is going to increase that normal force above mg. Because the net force, again, there has to be a net amount of force in the amount of mv squared over r. That's what the net force has to be. Right? So if mg is down like this is mg, again, then you're going to need a much larger force, so that when you subtract these, you subtract mg, this amount here, this bit is mv squared over r. The net has to be upwards. So it's always more. The normal force is always more at the bottom. And it's normally many times more than its weight. 2 times more, 3 times more. All right, that was that one. And then in which direction is the net force on the ball at the bottom and top of the loop? At the bottom, if they said draw just the net force on this free body diagram, it's up. And what does it equal? mv squared over r at the bottom. Because technically, it hasn't left the, if that track was bent around so that it kept going in circles, then it would be still circular motion. The net upward force has to be mv squared over r. How about at the top? At the top, the net force has to be down. F net would be also mv squared over r at the top. But the harder question is, which one would be bigger? The top or the bottom? Which one, in which case is the track pushing harder on the ball? At the bottom or the top? Technically, it has more speed at the bottom, because it's going to come around that top. It's going to go around the track and go down. That means potential energy is being converted into kinetic energy. You're going to have greater speed at the bottom. So if M and R are the same in both, when you compare these two, the only distinguishing factor is V. Wherever V is the greatest, it'll be larger. So the net force at the bottom might be like that, while the net force at the top, sorry, did that backwards. The net force at the bottom might be really large, like this, while the net force at the top might be like this. So you'd have more net force at the bottom. What will it be equal to? mv squared over r. I know it's confusing, but those values are not the same. M and R are the same, but at the top, V is not the same as at the bottom V. V at the bottom is bigger. This is why this would be a bigger arrow. All right, that's it, I guess. Where is the net force the greatest? At the bottom. All right, I am going to give you guys 25 minutes to work on this problem. You can work alone or by yourselves. I'd really ask you at this point maybe to work on by yourself. I'm still going to put you into groups. Like if you're totally stuck, I still think it's useful to be able to turn to somebody and ask a quick question. But I want you to start trying to think, can I get through this problem in 20 minutes? So I'm going to close this out. I'd like you to go to Google Classroom. If you, Matt, can jump in with us because you're always, well, everybody is, but I want everybody in it. The top says AP exam problem. And finally, you get to see a real problem, a real AP problem. Yeah, it's term 2011. In fact, it wasn't even AP Physics 1. AP Physics 1 wasn't even created yet. It was called AP Physics B back then. And I taught that. And I had to teach not only every chapter that I'm teaching you, but the whole second half of the book too. The whole book. And after many years of people complaining and saying, this is just way too much, we can't continue trying to teach this amount, we can't do it. They finally said, we're going to recreate new courses. We're going to just totally kill AP Physics B and bury it. And we're going to create new courses called AP Physics 1 and AP Physics 2. AP Physics 1 will be the first half of the book. That's what you guys are doing. And AP Physics 2 will be the second half of the book. That said, these questions are, this is totally a legit current, they could give a question just like this next year. These questions haven't changed that much. There is a little bit of change. I'd say that notice that it's heavy in calculation. You still could get some that are heavy in calculation, but they've leaned more towards concept. Notice that C, D, E, F, actually B, C, D, E, F, calculate, 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 calculate. And they were complaining about that, saying, it shouldn't be so many calculations and not enough concepts. But I'd still like you to try it because we can talk about the concepts afterwards, and I'd rather have my students be able to do all of it. So give it a go. It's there, and try your best to submit it by the end of class, which is 10:10, because I want you to really try. Can you do it in 20 minutes? This would be a 20-minute problem. If you don't have time to actually submit it, I get it, because you'd actually have to take a photo of it and upload it, and that takes some extra time. And I don't mind changing the due time from 10:10, but it's just trying to encourage you to try to do it now. And try to see, can I do it in 20 minutes? Again, if you have to image your work later, upload it a little later, that's fine. All right. I'm going to toss you guys into your groups. Let me know if you have, well, actually, no, just do your best. I guess that's where we're at. Do your best. Hi, William. Do you have a question? Are you in here still with me, William? William? Oh, he left. All right, it looks like everybody's back. So that would be 20 minutes. You know, that would be a moment where you would be thinking, I should probably move on to the next free response question. This would be in a free response portion of the exam. Again, you get 5 of them, but that would be the recommended 20 minutes where you start really considering whether you're going to, how much more time you'd spend on that. So please upload. I think I'll change the due time to, you know, I don't know, sometime maybe tonight. I just hope you guys all took the time to do it. Tomorrow, what I'm going to do is provide you with their rubric. Partly why I'm taking me a while to get back. I'm still working on these exams of yours. They don't give me rubrics for all the problems that are in AP Classroom. I have to make all my own rubrics, and it's takes painstakingly long for every little detail to be noted, created. Anyways, the ones that I just gave you, all those rubrics are online. So I'm going to be printing out their old rubric for that problem, and we're going to take a look at it tomorrow so you can better understand how they grade. But make sure you upload that work, today's work, by the end of the day. I'll change the due date so time till to tonight. Other than that, there's no homework for tonight. See you guys tomorrow. Have a good day.